steps required to write any program code for just about any machining operation are nearly identical. But for a facing operation, let's look at the specific steps necessary. We need to select a tool and an insert. We need to calculate the speed and feed. Then we need to consider all of the machining conditions that may override what is recommended for speeds and feeds. Then we will move on to perform any of the dimensional math needed, because not all the dimensions are on a blueprint. Sometimes we have to perform some calculations to find these missing dimensions. Then we will decide on a turret station as to where we're going to place this tool on the machine. Finally, we will write the program and check it. Tools that can be used for facing operations come in many shapes and sizes. The most universal tool is the 80-degree diamond turning and facing tool. This tool holder is universal in that it can be cutting along the x-axis or the z-axis or both axes. It is a very strong, broad-nosed tool, and the insert for the 80-degree diamond comes in many different coatings which allow for different cutting conditions, as well as different geometries on the top of the insert, which controls the chip breaking capability of that insert. All around, the 80-degree diamond is a very good tool to use whenever possible. In this photo below, you can see that this manufacturer is showing just a few samples of what are the many different types of tools that are available to use on a CNC turning center. Let's take a closer look at that 80-degree diamond turning tool. The 80-degree diamond tool has a 5-degree clearance on the leading and trailing edges. That is because the angle of the nose on that insert is 80 degrees. This means that the tool can cut effectively the same in turning and facing situations. Also, the broad shape of the 80-degree diamond is very strong, which allows for very heavy cutting conditions. Now granted, that may not apply in our finishing situations, but you will learn that the same tool is oftentimes used for roughing and finishing. A large tool radius allows us to feed at a high feed rate and still obtain a good finish. The 5-degree clearance along the bottom of the tool there also helps to wipe down the peaks that are created from the turning operation. This also enhances our surface finish. So the surface finish is not only controlled by the feed rate and the radius of the tool, but also by the clearance angle on the back side of the tool. When selecting an insert to use with the turning tool holder, you are much more concerned with the work material and the type of cut you are performing. Inserts have many different coatings. That's what gives these carbide tools the gold color. To select the proper grade of insert, you must check the catalog for your tools. In the catalog, they will recommend a certain grade of insert that holds up well for each type of work material. Many considerations come into play when talking about tool life. The coating on the insert, the workpiece material, the depth of cut, the feed rate, as well as the chip breaker design that is cast into the top surface of the insert. All of these factors play greatly as to how long your tools will last on the machine. Obviously, these tools can be very expensive, so you do want to get a certain amount of tool life out of this tool, but at the same time, you need to maintain high efficiency when machining, or your profits will suffer. Not only do you have many choices of grade selection, you will also have several choices of chip breaker geometry to choose from. The chip breaker geometry on a carbide insert is the bumpy surface on the top of the insert. Depending on the height and shape of these bumps, you can get different chip breaking effects. A good tooling company will offer many different styles so that you can choose one that works good with your material and cutting condition. Obviously, the depth of cut has a tremendous amount to do with which chip breaker you would choose. If you're taking a shallow depth of cut, you would select an insert where the chip breaker is closer toward the cutting edge of the insert. The heavier the depth of cut, the further back the edge is for the chip breaker. There are many other aspects to selecting that chip breaker, and fortunately, most good tooling vendors offer a great selection method with their tooling catalogs. These tooling catalogs must be referred to continuously when you are programming and processing a workpiece. For our facing operation, our facing depth of cut will be 35 thousandths in this example, and our work material is going to be 4140 steel. Where the depth of cut and the IPR cross is the chip breaker style we want when we're looking at this chart. So if we follow along the left-hand column of numbers, that is our depth of cut. So starting from the bottom, we come up to 25 thousandths. A little bit further up would be our 35 thousandths depth of cut. From there, we want to go towards the right until we finally meet up with our feed rate range in inches per revolution. Now that would be the row of numbers along the bottom of this chart, starting at 4 thousandths and going all the way up to 32 thousandths per revolution. We want to obtain a relatively good finish on this workpiece. And because this is a finishing operation, our feed rate is going to control the finish on the workpiece. If we select a 6 thousandths inch per revolution feed rate with an 80-degree diamond, we are going to get approximately a 62 micro finish, which is a relatively good surface finish. So if you watch the arrows, you will see that they converge on the chip breaker design labeled MG-LF. That would be a good choice for our particular cutting condition. You can see by looking at this chart that depending on our depth of cut and depending on our feed rate, we would end up selecting different chip breaker designs. Now these letters represent part numbers to the tooling vendor. So when you're selecting your inserts, you would not only select the geometry of it, meaning the 80-degree diamond or 55-degree diamond, and the radius of it, but we would also have to select the grade and the chip breaker design. Once you get the hang of this, it goes very quickly, and soon you will learn that certain inserts with certain geometries work great for you in many of your situations. On the previous step, we selected a chip breaker style MG-LF, and that was based on our recommended feed rate that we chose based on the finish that we want to achieve, as well as the depth of cut that we want to take with this finishing tool. With that chip breaker style and our cutting conditions, which would be a smooth cut as opposed to a heavily interrupted cut, such as the case of turning square stock, or lightly interrupted cut, which would be more along the lines of turning hex stock, and possibly varied depth, which would be material that is severely out of round, or perhaps even a casting, to finally a smooth cut. That would be a situation where you're finished turning a pre-machined workpiece. So in our example, we are definitely taking a smooth cut. So what we would want to do is go down the left-hand column, finding our insert geometry, and see MG-LF. We would follow that to the right, coming down from the smooth cut column located along the top. And where those two converge is the insert grade that this particular tooling vendor is recommending. In this particular case, it happens to be KC 9010. Now that we know our feed rate, 6 thousandths per revolution, our chip breaker design, our cutting condition, smooth, and our insert grade, KC 9010, we can then determine the cutting speed range. From that, we can then calculate a value that is in the middle of that working range. You will notice that almost all cutting tools have a recommended working range for a particular workpiece material. There are many reasons for this, but mostly you will notice that 4140 material comes in different hardnesses, and the harder the material, generally speaking, the slower the speed is that we need to cut it. Also, what controls the speed at which we're going to cut this material would be our depth of cut. The greater the depth of cut, generally speaking, the lower on the working range we would select. The lighter the depth of cut, the higher on the working range is where we would make our selection. For our example, what we're going to be doing is selecting a point about in the middle of that working range. This gives us a little bit of room to work up or down within that working range that is recommended for this tool. So we're going to come down the left-hand column and find our insert grade, KC9010. And then we're going to move along toward the right. And the yellow box that's outlined there for our smooth cutting condition starts out at approximately 600 surface feet per minute. The other end of that yellow box would be 1100 surface feet per minute. To calculate the midpoint of our working range, we would add those two numbers together and then divide by 2. And that gives us our starting point of 850 surface feet per minute. Now that we've gone through and calculated our 6 thousandths per revolution feed rate at 850 surface feet per minute, we must now look at what other conditions might exist that would cause us to alter or deviate from those recommendations. At the top of the list would be work holding. Certain workpieces cannot be held very well in the chuck. In situations where we've got less than ideal work holding conditions, we might want to back off a little bit on the feed rate and a little bit on the speed. If the machine condition is poor, if the bearings on the spindle are getting a little bit worn because of the age of the machine, it might not handle high RPMs very well, in which case we might need to slow down the speed. The horsepower of the machine. Now in finishing operations, we are generally not taking a heavy cut, so horsepower is usually not a concern. Tooling, in our particular case, we are assuming that we're working with good quality, good condition tools. If our tools are in less than good condition, we may need to back off on our speeds or feeds a little bit. And finally, the material condition. Is our workpiece material in pretty good shape when we start out with, or is it in marginal condition? This would be in a situation such as castings, where there is a lot of porosity or perhaps even cracks in the casting. If that is the case, then we may need to slow things down as well. What you have to watch for in any facing situation, either finishing or roughing, is we don't want to push the workpiece out of the chuck as this animation is demonstrating. Now granted, in a finishing situation, this would be rather difficult to do if the conditions were correct. However, if you look at the general operation that is being performed here and the way this tool force is being applied to that workpiece, it would want to push the part out of the chuck, whereas a turning operation would be pushing the part into the chuck. So generally speaking, we tend to be a little bit more cautious during facing operations with regard to the acceptable cutting conditions and other considerations relative to the machining operation. The nice part about programming a facing operation, especially a finish facing operation, is there is generally no math to do. When we are taking a finish facing cut, we almost always perform that at Z0, which is the rightmost finish face on our workpiece. The 1.25 dimension that is shown on the print, which specifies the overall length of the part is actually established when the setup person sets up the job. He would of course have to take that tool and touch it off to the workpiece and make a measurement from Z0 back to home position for that specific tool. And that's what establishes the overall length of the part. The 80-degree diamond that we're going to use in this example is a very common tool holder, and most machines would even have one station dedicated to this particular tool holder. For our example, we're going to say that that dedicated station on our turret is tool number 2. And that's what we're going to use for our finished turning tool station. Now that we have performed all of the steps necessary to write the program, and granted there were many, but as time goes on you'll learn that these go very quickly once you get the hang of it. For writing our program, it starts out with line number 200, which is a comment using the control in and control out characters, which are the left and right parentheses. In there we will describe to the setup person what tool number 2 is. In this case, it is part number DCLNR-164, and it has a CNMG 432LF-KC9010 insert in it. That is, by the way, the part number of the tool holder and the insert. Some shops will use more general descriptions here. However, you will find that either on the layout sheet or within the program itself there should be specific information. This way the setup person will not accidentally use the wrong grade of insert or even the wrong chip breaker. In either case, the cutting conditions may not end up being ideal, and he may have to then detune the program to accommodate the wrong tool. Moving on to line number 210, we simply call up tool 2 with offset 2. Line number 220 calls up G96 constant surface speed mode, S850 specifying 850 surface feet per minute, and turns the spindle on in forward rotation with our MO3 command. Line number 230 puts the machine into rapid mode with G00 and rapids to the diameter of X 4.1 and the Z position of 0.1, which is 100 thousandths away from the front of our part, and turns on our coolant with the MO8 command. Line number 240 rapids the tool to Z0. Line number 250 goes into linear interpolation mode with the G01 command and feeds down to X of minus 0.032 at a feed rate of 6 thousandths per revolution. You will often see programmers face a part off past the center line, and that is noted by the X negative value. That would move the tool past the center line of the part. The reason for this is it oftentimes helps to eliminate a nib that is left at the center of the workpiece. Keep in mind that if we face the part off to X0, only the bottom edge of the tool will be at X0. The remaining radius of the tool would not have cut all the way down to X0. This results in a little nib that is oftentimes unacceptable to a customer. Going on to line number 260, we rapid the tool with the G00 command to a position of Z.1, which is 100 thousandths to the right of the workpiece. Line number 270 rapids the tool back up to X of 4.1, which is 4.1 inches in diameter. Line number 280 rapids the tool to a diameter of X 6 inches and Z of 5.5 inches away from our workpiece. That would be considered our safe tool change position on this particular machine. Line number 290 sets the machine into the optional stop mode, at which point the machine would stop, allowing the setup person to check the workpiece. Of course, this being the optional stop command, the machine would only stop if the optional stop switch were turned on. Here you can see this program being brought to life by the animation. Watch the tool motions and try to match them up with which program command is moving the tool to that particular position. When you're finished with this, move on to the next slide, and we're going to take a look at another finish facing operation performed on tubing. When we are facing parts that either have a hole already in them, such as tubing, or perhaps a pre-drilled hole, we only need to account for the fact that we're not going to feed all the way to the center line with the facing tool. This would just simply waste time. However, from our years of experience of watching and helping beginners, we have seen mistakes made many times where the programmer would program the tool to feed all the way to the center line, simply wasting time. Other than the fact that we don't need to face to the center line, facing tubing is exactly the same as facing bar stock. So we're just going to jump right into the program using the same cutting conditions as our bar stock example shown previously. This is basically the exact same program we used in the previous example. However, you'll notice that on line number 250, we are feeding with the linear interpolation command G01 to a diameter of x 1.2 inches at a feed rate of 6 thousandths per revolution. You will notice that the hole that's already in the workpiece is 1.25 inches. So all we're doing is just facing a little bit smaller than the hole that's already in the workpiece. We don't want to feed to the center line, as that would waste our cycle time. Here you can graphically see what is different about how this program executes. You will notice that the tool does not go all the way to the center line, but that it stops short of moving to the center line by just feeding past the bore diameter. Programming a facing operation for castings and forgings presents a new problem in that they are not all the same size. Depending on the quality of the casting, variances of up to 125 thousandths of an inch from part to part are not uncommon. A good program is designed to handle these variances in part size. To handle that, what we need to do is be a little bit more cautious on our approach move when we move up to the workpiece to position the tool for the finish facing cut. Our facing depth of cut will be 60 thousandths of an inch in this example, and our work material is going to be ductile cast iron. Again, we use the feed rate of 6 thousandths per revolution to achieve an approximate 62 thousandths microfinish. For this particular tooling vendor, they basically only have 3 geometry chip breakers that they recommend for working with the cast iron grade. In this example, they're showing MA, MG, GA-T. So our choice is truly quite simple. We only have one chip breaker geometry to choose from. But nonetheless, if we were to follow this chart, we would start with our depth of cut range along the left side of the chart and find 60 thousandths of an inch. And we would draw a line to the right from there. We would then come up from the bottom of the chart, selecting our feed rate and going up. And where those two lines would cross would be the chip breaker style that we want to use for our application. On the last step, we selected from the choices a chip breaker style of GA-T. In the row marked GA-T, I find the column for the varied depth of cut, which is generally the case for castings and forgings, and we select a grade of KY 3400. Again, we would start at the left side of the chart, finding our insert geometry, GA-T, and we would go towards the right, looking at the top headings of each of those columns: heavily interrupted, lightly interrupted, varied depth, or smooth cut. A casting would truly be a varied depth of cut. So that's where we would meet those two lines, and we would come up with KY 3400 as our insert grade. With consideration to our cutting condition, varied depth, and the insert grade we selected, KY 3400, we can then determine the cutting speed range. From that, we will calculate a value in the middle. By using the chart below, we would follow along the left-hand column for our grade and find KY 3400. And we would move towards the right looking for the blue box, which is our varied depth of cut range. And we can see that it starts from 1450 SFM and it goes all the way up to 1900. So we add those two values together, divide by 2, and we come up at 1675 SFM. (1675 SFM is very high, so we should check to make sure that our machine is even capable of cutting at that high of a speed. For this machine, we will say that our maximum RPM is 4,000 RPM, and in my opinion, the Workholding 3-jaw chuck can hold the parts securely at that RPM. Using the formula 3.82 times the SFM divided by our cutting diameter, we can get our RPM. So we take 3.82, our numeric constant, and multiply that times 1675, which is our SFM, and then we take that result and divide it by 2.25, our cutting diameter, and that comes up with 2,843 RPM. That's well below the maximum allowed on our machine. If the RPM would have calculated higher than 4,000 RPM, we would have had to gone back to the beginning of that tool selection process and selected a lower speed grade that would allow us to cut efficiently with that tool at a lower spindle speed. The Workholding can be a problem when holding castings or forgings, as they are not perfectly smooth and round. A 3-jaw chuck can hold parts securely, but as the shape of the part deviates from perfectly round and smooth, its ability to hold the part diminishes. Hardened points or grippers are often added to jaws so that they can bite into the part and provide a much better work-holding condition. This method can also be used on other parts where work-holding is marginal and heavy roughing is performed. We have seen this used in billet applications as well as in shaft applications. Hardened points really enhance the work-holding capability of a chuck, and in heavy roughing situations they can really make the difference between profit and loss on a workpiece. Now let's walk you through the program itself. On line number 200, we are describing the tool as we did before. We specify which tool station the tool is going to be placed in. We give the tool holder number DCLNR-164, and then we describe the insert, CNMG-432 GA-T-KY 3400, which is the insert grade. Line number 210 simply calls up tool 2 with offset 2. Line number 220 sets the machine into constant surface speed mode with the G96 command, specifying a spindle speed of 1675 surface feet per minute, and turning the spindle on in forward rotation with the MO3 command. Line number 230 puts the machine into rapid motion, G00, and rapids to a diameter of X 2.35 and a Z position of Z.1, and we turn the coolant on with MO8. A quick side note here is that not all carbide inserts recommend the use of coolant when cutting cast iron. Be sure to check the documentation carefully in your tooling catalog when you select your insert grade. If you cut with coolant on cast iron with certain carbide inserts, you may find that the tool life is very, very poor, or the tools may actually self-destruct immediately during cut. So please use caution when working with coolant cast iron, and certain cutting tools. Moving on to line number 240, we can see that we are now going to feed to Z0 at our feed rate of 6 thousandths per revolution. In our past examples, we made this motion as a rapid motion. This was because the workpiece condition was much more round and on size. Castings, with their great variances, we have to make a provision that the part may not be the exact size that we thought it was when we write the program. So to account for that, if the part is a little bit bigger in diameter at this stage of the game, the tool would safely feed onto the workpiece here and then move into its facing cut on line number 250. Line number 250, still in linear interpolation mode with the G01 command, feeds the tool to X of minus 0.031, which will again face off the workpiece and make sure that we eliminate that little nib at the center line of the part. Line number 260 rapids the tool away from the face of the part. Line number 270 will rapid the tool back up to a diameter of X 2.35. And then finally, line numbers 280 rapids the tool to a diameter of X 6 inches and Z of 5.5, which would be considered a safe tool change position for this particular machine. And then line number 290 providing the optional stop command. While we are talking about this particular program, I want you to look at the different colors on the screen that we've selected for this program. The blue section near the top of the program is our tool startup information. Now the format of that and the structure of that would definitely change from one machine to another, especially if they are made by different companies. However, you can see that this is the basic information needed. We describe the tool, call up the tool with an offset, get the spindle running, and get the tool into position for our cut. The green section of the program is our actual cutting data, the movements necessary to face the part off. And finally, the program ending information, which is the black text portion of the program, gets the tool back to the tool change position. Sometimes you may see the G28 U0 W0 command at this point. That would of course send the tool to its home position where we would change the tools. This area of the program, the tool ending section, definitely varies a lot from one machine to the next. So be sure to pay close attention to the programs that are written for the machines at your company or in your department. Watch this animation carefully and you will see that the tool is feeding along the Z-axis after it approaches the workpiece and just before it goes into the facing cut. That is the subtle difference between facing off a casting versus facing off a billet or a piece of tubing. All we are doing at that point is just preparing ourselves so that the tool can feed on in case the part is not exactly the size that we predicted when we wrote this program. If we were to not do this, the tool could actually rapid in that motion, hitting the workpiece. This could cause a very serious crash to the machine, or at minimum probably break the tool. Either condition causes an unsafe condition and we don't want that on the machine. Watch this animation carefully and you will see that the tool is feeding along the Z-axis after it approaches the workpiece and just before it goes into the facing cut. That is the subtle difference between facing off a casting versus facing off a billet or a piece of tubing. All we are doing at that point is just preparing ourselves so that the tool can feed on in case the part is not exactly the size that we predicted when we wrote this program. If we were to not do this, Now that you got a taste of the finishing operations, let's turn our attention to drilling operations. Drilling a hole with a CNC turning center is one of the most basic machining operations. However, oftentimes the drilling operation is oversimplified and poor efficiency is the result. This can manifest itself into poor cycle times and/or poor tool life. Let's take a look at one of the more correct ways of programming a drilling operation. In this example, we can see that we need to drill a 3/4 inch diameter hole 3 inches deep. As with any machining operation, we need to perform all the required steps to program the operation. We need to select the tool, calculate the speed and feed, consider all machining conditions, perform any dimensional math, decide on a turret station, and finally write the program and check it. To drill this part, we will use a 3/4 inch diameter high-speed steel drill bit. High-speed steel drills come in many different varieties with regard to flute geometry and coating materials. For this example, we will use an uncoated high-speed steel standard twist drill. As with all machining operations, we must calculate the speed and feed. To do this, we will refer to a chart that has our drilling SFM for our workpiece material and our feed rate for each of the different size ranges of drills. Depending on the diameter of the drill, it can handle a different amount of chip load. If you look at the chart, you'll see that the lowest feed rates are for the smallest drills. The larger the drill, the heavier the feed rate. In our example, what we are going to be drilling is brass. So what we can do then is come down that left column where it says work material and find the material brass. Going toward the right to the next column labeled SFM, we can see that our feed rate is going to be 140 surface feet per minute. Continuing to the right along that same row where it says brass, we are going to line that up with the column labeled IPR, and it has a 3/4 inch for 3/4 inch diameter drill. And we can come across that row and column and we line up with a 10,000ths feed rate. Now if the drill fit into a size range that was between 1/2 and 3/4 inch, we would use a feed rate that would be between that range as well. Drilling occurs at the X position of X0, which is the center line of the part. Mechanically, this is the only X position we can drill at. If the machine were programmed in constant surface feet per minute, the spindle would run at maximum RPM because we are positioning the tool at a diameter of 0. Because of this, we have to program the drilling operation in direct RPM as opposed to SFM. The reference chart that we looked at gave us the SFM for the proper cutting speed of this tool. We need to calculate the RPM. To do this, we can use a very simple formula. You might want to write this one down and try and memorize it because it is something that is used over and over again. The formula is this: RPM equals 3.82 times the surface feet per minute divided by our cut diameter. In our example, 3.82, our numeric constant, times 140, our SFM for this cutting operation, and then we will take that result and divide it by 0.75, and we should come up with 713. Now this is the S command, so we would round off the number to the nearest whole number and not worry about any decimal portion of that. Now we must consider all of the machining conditions and determine if we should stick with the recommendations or override them for our application. We would consider things such as our work holding, the workpiece material, machine condition, horsepower, etc., and we will consider all of these as good and capable in our application. With a 3/4 inch drill, that can be machined on almost all CNC turning centers. If the drill were a little bit larger in diameter, say 2 or 2.5 inches, then we might start running into horsepower problems. Another possibility is if we are drilling a very hard material, then we might end up pushing the part back inside of a collet during a bar feeding operation. This is quite common. However, the main considerations for drilling would be spindle horsepower when working with very large diameter drills, possibly the horsepower for the Z-axis thrust, which would come from the Z-axis servo motor. It might not have enough power to push the drill into the part, in which case it would stall the machine, giving us a servo overload alarm. And then finally, the work holding would be in a situation where we are working with a bar feed application, and when we're drilling with a large diameter drill into a relatively hard workpiece material, the bar stock might slide back into the collet. This can happen, and it does happen frequently when working with hard materials. The depth of the hole relative to the diameter of the tool is marginal, but it should work. When the depth of the hole is more than 3 times the diameter of the drill, you should back off on the speed and sometimes the feed rate by 20 to 30%. In our situation, we have a 3/4 inch drill, which is a little bit less than 1 inch, and we're going 3 inches deep. So it is marginal, but we should be okay in this application as we are drilling brass. The dimensional math required for drilling is generally very simple. Most blueprints will specify a hole depth as shown below, or with a simple statement such as 3/4 inch drill, 3 inches deep. Note, however, the depth is in reference to the full diameter of the hole, excluding the drill point. We must calculate the length of the drill point so that we can make sure that the 3-inch depth is a full 3/4 inch in diameter. In other words, we must drill deeper than the print shows in order to compensate for the drill point. This is something that we have to calculate using mathematics, and we have to change our program so that it drills deeper. Now keep in mind, what we're going to do is calculate the length of the drill point based on a theoretical angle. Oftentimes, drills are not ground to a perfect angle. Most drills are ground to a standard angle of 118 degrees. This angle, as shown below, is called the included angle, and this is the proper way to specify the angle on a drill. What we will be using in this example is an 118 degree included angle drill. For other angle drills, we would have to go through a different process for calculating the point length. To calculate the drill point length for standard drill points, which means a 118 degree drill point, we can use the simple formula 0.3 times the diameter, and that would equal our point length. So in our case, we're going to take a 3/4 inch drill, so we will use our formula 0.3 times 0.75, and that equals 0.225, and that would be our point length on this drill. Now, of course, that's assuming that the drill is ground proper, but it is our best protection and our only protection when writing the program, as we don't have the physical tool always in front of us. But if we program for a properly ground drill, we should be okay. The setup person would definitely adjust this during the setup. Now we must add the point length to the hole depth as specified in the blueprint. The blueprint shows a 3-inch depth, which would be the full diameter of the hole to a full 3-inch depth. We would add 3 inches plus our 0.225 that we calculated in that previous step, and we would end up programming our drill to drill 3.225 deep. Most programmers will dedicate certain stations on the turret of the machine for certain types of tools. This helps to reduce setup times because the setup person will not have to switch tool blocks from one location to another on the turret for each setup. For our example program, we will say that turret station number 5 will be used for our drilling station. As you can see by this program, it is really quite brief and quite simple. The first line, we are going to describe the tool. Tool number 5 equals 3/4 inch high-speed steel drill. Sometimes it is important to include a tool length on this description as well when you are drilling a relatively deep hole that might exceed the length of a standard length drill. Line number 500, we call up tool 5 with offset 5. Line number 510, we put the machine into direct RPM mode with the G97 command. Now that's the first time you've seen that used in our example programs, but that's all there is to setting the machine into direct RPM mode. Then we have our S713, which specifies 713 RPM, not SFM. Finally, we have our MO3 command to turn the spindle on in forward rotation. Line number 520, G00, X0, Z.1, MO8, rapids the tool to X0 and a position of 100 thousandths away from the front of the part, turning on the coolant. Line number 530 feeds the tool to our depth of 3.225 inches at a feed rate of 10 thousandths per revolution, and we are of course doing this in linear interpolation with the G01 command. Line number 540 rapids the drill back out of the part and positions it 100 thousandths in front of the part. Line number 550 rapids the tool back to our tool change position of X 4.5, Z 2.5. Now again, that line would be customized for each specific machine and sometimes each specific job that you would program. And finally, line number 560 is our optional stop command. Truly a very simple machining operation, but nonetheless, if it's not performed correctly, you can have very poor tool life and poor machining efficiency. Here you can watch the program run fully animated. That previous example was drilling at its simplest. Let's take a look at what to do if the drill point is not 118 degrees and how carbide tip drills can really save time and money. In a later lesson, we'll also look at how to peck drill when drilling holes that are very deep relative to the diameter of the drill. The method and process of programming drilling operations is basically the same for all parts. Review the information below as it serves as a good guideline when writing programs. The steps to perform are: select the tool, calculate the speed and feed data, consider all machining conditions, perform the dimensional math, which usually is a case of calculating the point length on the drill, decide on a turret station, and finally write the program and check it carefully. Some of the common machine features that are used: you will always use tool startup information as with any other tool. You will always drill at X0 unless working with some carbide drills which allow you to drill off-center, and that is a indexable insert carbide drill. We would also use the RPM mode always, and we would feed in inches per revolution. And finally, as with all other tools, it would use the tool ending information for our specific machine.